Hello, everyone. My name is Olga, and I would like to welcome you all to this webinar organized on behalf of IOSH Environmental and Waste Management Group and Royal Society of Chemistry, Process Chemistry and Technology Group. The topic of today's webinar is the challenges of nuclear waste in the UK, and it will be presented by Dr. Carl Steele. Carl has a PhD in chemistry from Newcastle University and more than 23 years of work experience at British Nuclear Fuels, now known as Sellafield. In 2019, Carl joined Orana to lead UK waste consultancy team and most recently moved to Atkins Limited for a new role in waste management consultancy. Carl also a chartered chemist, and he is a fellow of Royal Society of Chemistry. And today he will be sharing his knowledge with the IOSH community. This is the first webinar on this topic organized by our group. And in the end, you will be able to vote, to complete a survey to vote for the next topic on this series. Please do put your questions in the chat and we will be able to answer them in the end of our session. Carl, please join us. Hello, Carl. Could you please share your screen with the presentation?
Oh, here. There we go. Can you see that?
Yeah,
fantastic.
Thank you.
Brilliant. So thank you for giving the opportunity today to talk a bit about the nuclear waste. So I'm here also on behalf of the Royal Society of Chemistry Special Interest Group, the Process Chemistry and Technology Group. I've worked in the nuclear waste management for over 26 years. Previously worked at Sellafield in West Cumbria, which is a nuclear licensed site, working in both thermal oxide reprocessing of used nuclear fuel and also waste vitrification to treat highly radioactive waste using vitrification treatment to convert waste into a safe and passive form for long-term storage pending geological disposal. Currently working in nuclear waste management consultancy with Atkins, working with a range of different clients covering the full nuclear fuel cycle, including new build, fusion, waste handling, waste disposal, and enabling the decommissioning of existing nuclear facilities across the UK. So here are the learning outcomes in the presentation. So the purpose of this presentation is to share knowledge in nuclear waste in the UK, what key principles are used in the management of nuclear waste, to talk a bit about the composition of radioactive waste, its variety, and this presents a number of different challenges. I'll also cover some aspects of how radioactive waste is safely treated and disposed of, and you'll also learn a little bit about the types of disposal routes for nuclear waste, which contain different compositions of radionuclides. I've got a short video from the International Atomic Energy Authority, just to show you, to give an introduction to radioactive waste.
Waste is an unavoidable consequence of everyday life. In terms of volume, radioactive waste is a very small portion of all waste. It's the byproduct of millions of medical procedures each year, industrial and agricultural applications that use radiation, and nuclear reactors that generate around 10% of global electricity. Radioactive waste requires careful management to protect people and the environment from radiation now and in the future. Radioactive waste is first characterized to determine its physical and chemical properties, as well as its radioactivity. It's then processed, which may include sorting, decontamination, and steps to reduce volume. The waste is classified based on its long-term management objectives and put into a safe condition for interim storage and ultimately disposal. Very low-level waste and low-level waste contain small amounts of radioactive substances. It includes waste generated by industries and hospitals or items such as clothes used in nuclear facilities. This waste requires minimal isolation and is suitable for disposal in near-surface facilities. Intermediate level waste is more radioactive and typically comprises materials from decommissioned reactors and research laboratories. It requires more containment and isolation. High-level waste presents the greatest hazard. It accounts for a minute portion of the total volume of all radioactive waste and includes waste from nuclear power plants. High-level waste requires greater containment, and its disposal is planned in engineered facilities several hundred meters underground. In the meantime, it is safely stored in purpose-built facilities. The IAEA provides support to countries in the safe management of all radioactive waste.
So, here's a summary of the key aspects that we covered in the webinar today. I've also included a slide at the end of this presentation for future suggested topics as well, which may be of interest to participants. So we refer to nuclear waste as radioactive waste because of its radioactive nature and its composition of radioactive materials. I'll cover the categories and classifications of radioactive waste and its management and controls. There are also a number of different treatment technologies as well and methods for treatment to safely dispose of waste. And then I'll cover some of the different disposal options for radioactive waste and the future challenges. So basically a brief history of nuclear waste in the UK. So the United Kingdom is a pioneer of nuclear technologies, which have been a part of our daily lives for more than 60 years now. Nuclear power has delivered great benefits. It has supported national defence, generated electricity for more than 60 years, and our country remains a world-leading nuclear enterprise. Nuclear waste has arisen from the production of nuclear fuel to be reprocessed to produce fissile material for nuclear weapons, followed by the development of the civil nuclear power reactors to provide energy and also radionuclides for medicine. The UK is now faced with the challenges of cleaning up the legacy of its early nuclear operations. So this is a large-scale programme currently being undertaken by the Nuclear Decommissioning Authority as part of the UK government. The UK government policy is to have a wide mix of energy supplies so we can use nuclear alongside other energy sources such as gas and solar. Today, nuclear energy generates around about a fifth of the country's electricity, and there's plans to replace the existing nuclear fleet, so with new builds such as Hinkley Point C and Sizewell C currently in design and construction. There's also an international consensus that geological disposal is the safest and most secure way in which to manage high reactive waste for the long term, and that a geological disposal facility will ensure that the responsibility of continually protecting this waste is not passed on to future generations. So where are these nuclear facilities in the UK? The radioactive waste resulting from power generation, medicine, defence and other industries needs to be managed carefully. So there are many licensed nuclear sites across the UK. The Atomic Energy Authority was established operated by the UK government from 1946 until the 1990s at Harwell in Oxfordshire. It was the host to provide the underlying science and technology behind the design and build of Britain's nuclear reactors and technology to obtain fissile material as well for the UK nuclear defence programme. The UK's first full-scale nuclear reactor was the Windscale Pile at Sellafield in West Cumbria, which was designed in the 1940s and operated until the Windscale fire in 1957. In Scotland at Dounreay, in the northernmost part, the UK government used a site to research and develop the fast reactor programme in the 1950s. There's also at Dounreay a Vulcan naval reactor test establishment, which is a military submarine testing facility, and 10 sites across the UK where the Magnox reactors have been built and operated. Calder Hall in Cumbria was the first commercial nuclear power plant, and this operated from 1956 until 2003. The advanced gas-cooled reactors, as AGRs, started construction at Hartlepool since operated since 1968. From 1983 to produce nuclear power. So these are still operating today. We have 4 sites of AGRs in the UK, which will continue to operate until 2026 to be retired from service by 2028. Springfields in Lancashire is a nuclear fuel production installation at Solwick, and it's been manufacturing nuclear fuel since the mid-1940s. In Plymouth, so Plymouth Dock, as Devonport was originally called, began around 1700. It covers 4 miles of waterfront to maintain the Royal Navy fleet and also provides services such as installation, maintenance and testing. The UK nuclear fleet of submarines are currently maintained there, and it also stores the retired nuclear submarines pending defueling and disposal. Sellafield in West Cumbria is a large multifunction nuclear site close to sea scale on the coast of Cumbria. Currently, its primary activities are nuclear waste processing and storage and nuclear decommissioning, and this has operated since the 1940s. At Culham in Oxfordshire, the Culham Science Park is the host to the Culham Centre for Fusion Energy, and this is the site of the Joint European Torus and Mega Amphia spherical tokamak. The existing waste is currently stored above ground at more than 30 sites across the UK. These surface stores can be safe for many decades, but require continuous protection to keep them secure and in good condition, as the waste remains radioactive for hundreds of thousands of years. So, where does nuclear waste come from? So obviously there's a variety of different sources. So besides nuclear power, radioactive waste comes from medical, in particular radioactive materials, which are used to sterilize equipment and help to diagnose and treat medical illnesses. From industry, such as an example of gamma rays used to test the quality of welds or thicknesses of product, such as paper. In defence, this includes operations of active nuclear power submarines and the decommissioning of the retired submarines. And also in research and development as well, from nuclear fusion technology to developing new radiotherapy treatments, as well to testing novel solid materials for encapsulating liquid radioactive waste. So how is the radioactive waste managed in the UK? So this is an overview of the UK legislation. So the fundamental aim of the UK policy and regulatory framework is that radioactive waste is managed in a way that protects the public, the workforce and the environment, and safeguards the interest of the existing and future generations and the wider community in a manner that commands both public confidence and takes due account of the costs. The International Atomic Energy Agency and International Commission on Radiological Protection are not regulatory bodies, but they are acknowledged experts in the field to inform government policy and regulation. The international organisations provide guidance and recommendations that get transplanted then into national law. The laws and regulations of these are controlled through the UK government. Other countries choose to define their waste differently, and the laws and regulations typically provide licensing of various aspects of nuclear activities, the government oversight and setting standards both for technical and environmental, and protection of human health from radiological and other hazards. In the UK, the nuclear industry complies with the ionising radiation regulations, the Nuclear Installations Act and the environmental permitting regulations. So this diagram doesn't include some of the details about the Scottish and Northern Irish devolved legislation. So in terms of what is classified as radioactive waste, so the definition of radioactive waste is provided here in the slide, and there's a minimum level of radioactivity which defines whether a material is then classified as radioactive waste. This is known as the clearance level and covers all of the different types of radioactive emissions. So how is radioactive waste categorised? So the different categories of radioactive waste, these range from very low level, intermediate level, and high level. These are categorized based upon the radioactivity measured in units of becquerels per unit mass. So for very low level waste, this is 4 becquerels per gram. So for low active, low level waste, this can range from greater than 4 becquerels per gram to less than 200 becquerels per gram as aggregate, or 1,000 becquerels per gram for a single object which is suitable for disposal. Waste can be disposed of at Sellafield at the Calder Landfill Extension Segregated Area, Clifton Marsh, Kingscliff and Dounreay also have approved sites for low-level waste disposal. Low-level waste needs to be, if it's greater than these limits, but less than 4 gigabecks per tonne of alpha emissions, or less than 12 gigabecks per tonne as beta gamma. That's suitable for disposal at the low-level waste repository near Drigg. If the waste has a higher activity than this, that waste is currently being stored, and this waste will be disposed of in the future in some form of geological disposal. So short-lived and long-lived radioactive waste. So we have a distinction between what we define as short-lived and long-lived waste, which is relevant for disposal considerations, since short-lived isotopes may be suitable for interim storage to allow for the radioactivity to reduce to lower levels to be managed more easily. We've chosen a limit of 30 years to classify between short-lived and long-lived, and this represents the half-life of cesium-137, which has a half-life of 30.17 years. Long-lived radionuclides, such as things like iodine-129 or carbon-14, have really high half-lives, so 15.7 million years for iodine and 5,730 years for carbon-14. Iodine-129 as well is one of 7 of the long-lived fission products that are produced in significant amounts, and it generates yields of about 0.7% per fission of U-235. So what does it look like? So this takes many forms depending upon the physical and chemical characteristics. So packaging as well, which is also dependent on radiological characteristics, greatly alter the appearance and handling properties. So the goal is basically to move from a dispersed, uncontrolled, unpredictable material to a secure, clean, safe waste package with predictable performance in a disposable environment. So nuclear waste, which has not undergone conditioning or treatment, is known as raw waste. So what it should like when it's been properly disposed of is that it goes into well-packaged, clean and safe packages. So you can see here the photographs on the slide. So the top left is the Barclay Vault. The bottom left is a Sellafield fuel pond. The top right is another Barclay Vault waste processed into 500-litre stainless steel drums containing intermediate level waste. And then we've also got another one on the side entry, a diagram cut through. We can't see that one. A bottom right is a 500-litre drum with a showing that what a package looks like containing ILW. So as well, there's some more pictures here. So waste is not often neatly and clearly labelled. So we have drums of what we call stuff, which is miscellaneous radioactive waste. So used reactor fuel is stored in fuel storage ponds, which are large lagoons, and the water provides radiological shielding for neutron emission. These ponds have decades of history, and records may either be missing, or we have missing information, or it may be difficult to validate the information. Unknown material as well may be stored on nuclear sites. So you can see on the top left is a shaft at the Dounreay site. The bottom left is a bunker 5 at Hunterston A of old radioactive graphite and metallic waste retrieved from a solid active waste bunker retrieval project. The top right shows a Sellafield cooling pond holding spent nuclear fuels in stillages. And the bottom right is Bradwell decommissioning waste, which is swarf from reactor fuel. So nuclear waste inventory. So just to say that the total volume of radioactive waste that exists today or is forecast to be produced is somewhere in the region of 4.56 million cubic meters. This is equivalent to about 4.9 million tonnes. Around 4.3 million cubic meters have already been produced, which equates to the 96% of waste that have been generated. There is a further 4% to be produced based on the current nuclear facilities, so this doesn't include future ones. The largest production of nuclear waste has come from the operations at Sellafield. The Magnox nuclear fleet as well has generated a significant amount of nuclear waste, included from advanced gas cooled reactors and pressurized water reactor operations. So high level waste is generated from the reprocessing of spent nuclear fuel at Sellafield. It is initially produced as a concentrated nitric acid solution containing waste fission products. The 2019 inventory of this waste includes the nitric acid solutions awaiting conditioning in the waste vitrification plants, some insoluble fission products that settle in storage tanks, tank lid heels, and also the glass product of conditioning, and small quantities of contaminated plant items as well, so mostly metallic and ceramic in material. So intermediate level waste. So the major components are steel, graphite, concrete, cement, sand, sludge, ion exchange resin, and flocculant. There is a wide range of steel items, including plant items and equipment, fuel cladding, and reactor components as well. Most graphite is in the form of moderator blocks from the first stage of reactor dismantling at Magnox and AGR power stations. The majority of waste reported as cementitious material is cement associated with conditioning of waste. The remainder is mostly higher active concrete from decommissioning of buildings. This is obviously defined with a specific activity above 12 gigabecs per tonne, measured in beta gamma radioactivity emissions, or 4 gigabecs per tonne of alpha emissions. It generally has a dose rate of greater than 2 millisieverts an hour and requires some form of shielding, but there's no requirement for heat dissipation. So in terms of low-level waste, the major components of low-level waste are generally building rubble, soil and steel items, such as framework, pipework and reinforcements from the dismantling and demolition of nuclear reactors and other nuclear facilities as well, and the cleanup of nuclear sites. Low-level waste comprises of miscellaneous contaminated waste from the operations of nuclear facilities, which is mainly scrap metal, plastic and paper. And low-level waste contains enough radioactive material to require action for protection of people, but not so much that it requires shielding, handling or storage. So very low-level waste. So the major components of very low-level waste are building structural materials, so principally concrete, brick, metal and other materials from dismantling and demolition of nuclear facilities. There are also small quantities of excavated soil from construction and demolition activities. So some of the key radionuclides which are quite challenging for treatment and immobilization. There's a range of radionuclides which are either easy to measure, difficult to measure, or impossible to measure. Spent nuclear fuel contains volatile radionuclides as well, highly active gamma and neutron emitters, and other radioactive materials that currently have no planned future use. Volatile and long-lived radionuclides are very, very challenging to treat and prevent further future release. So radioactive nuclides such as iodine-129 and iodine-131 Iodine-129 is a long-lived radionuclide, whereas Iodine-131 has a half-life of about 8 hours, so will decay very quickly. So this allows for spent fuel to be stored in storage ponds for a minimum of 6 months before requiring reprocessing to allow volatile radionuclides such as Iodine-131 to decay away. Tritium as well is a beta emitter. So it's used in significant abundances, such as things like CANDU nuclear reactors and fusion reactors, but is generally a low abundance byproduct in normal operations of nuclear reactors. However, it is highly mobile where it's found. It's classified as a short-lived radionuclide because it has a half-life of 12.3 years. Carbon-14 as well is also a beta emitter. This is highly mobile and is generated in graphite moderator reactors such as AGRs. Gamma emitters such as cobalt-60, americium-241, and cesium-137 are generated in significant quantities during thermal fission in nuclear power generation. And you may not be aware, but it is recommended that everyone has at least one source of americium-241 in their home in the form of a smoke detector. So a smoke detector typically contains 5 milligrams of americium-241, which is essential for alpha emission to prevent the smoke detector alarm sounding. So obviously, when you do have a fire, the dust particles enter the smoke detector, the alpha emission is interrupted, and the detector then goes into alarm. High activity, such as radionuclides such as strontium-90, which is a beta emitter and produced during nuclear fission in significant quantities. Its radioactive activity can be masked where there's in the presence of other gamma emitters. And I'm also going to be talking a bit more about uranium and plutonium. They'll be covered later in this presentation. So in terms of the waste hierarchy, so the adoption of the waste hierarchy was embedded in waste in England and Wales from regulation in 2011, and the UK policy for the management of solid, liquid and gaseous radioactive wastes. So this is a simple hierarchy to prevent the generation of waste, minimise waste generation, either reuse or recycle radioactive materials where this is possible, and only dispose of radioactive wastes as the last resort. So the benefits of applying the waste hierarchy. So there are several benefits highlighted in the slide to applying the waste hierarchy, which includes both hazardous and radioactive wastes. So other key factors as well, which are applied to nuclear waste management. The term as low as reasonably practicable. So a LARP guidance states that the requirement for risks to be a LARP is fundamental and applies to all activities within the scope of the Health and Safety at Work Act of 1974. This is important as there's a need to ensure that licensees meet the requirements where this is applied. In simple terms, it's a requirement to take all measures to reduce risk where doing so is reasonable. In most cases, this is not done through an explicit comparison of costs and benefit, but rather by applying established relevant good practices and standards. The development of relevant good practices and standards, including a LARP considerations, in so many cases, meeting them is sufficient. In other cases, either where standards are relevant, good practice are less evident or not fully applicable, the onus is on the licensee to implement measures to the point where the costs of any additional measures in terms of money or the time and trouble of effort would be grossly disproportionate to the further risk reduction that would be achieved. There's another term, so best available technique, so BAT. This means the latest stage of the development of processes, facilities or methods of operation which is practicable, suitable and appropriate to limit the waste arisings and disposals. So BAT guidance states that before granting or signifying any variation in authorization, the appropriate environment agency will wish to ensure that a systematic and proportionate examination has been made of the options for waste management, having regards to the waste hierarchy, and that the waste management strategy chosen represents the optimum to provide a proper protection for people and the environment. Waste management strategies should be determined by the application of BAT or best practicable means as appropriate to the legislative regime. So in terms of the waste management life cycle, where nuclear waste is generated, this will dictate its radioactive composition, known as the radioactive waste stream fingerprint. Pre-treatment of nuclear waste by the means of sorting, segregation, conditioning, and containing waste. Generally, nuclear waste may be categorized by the predominant short-lived and long-lived radionuclides. For waste containing short-lived radionuclides, it's possible to allow for short-term decay during storage. For example, as I mentioned, used nuclear fuel stored over 6 months primed to be reprocessed to allow for the decay of iodine-131. Waste containing long-lived radionuclides will require treatment and conditioning to minimize the waste, the volume of waste generated, and to prevent radionuclides from being ingested, inhaled, absorbed to cause harm to people in the environment. And the main waste arisings, so the major categories of liquid and solid waste arising from the nuclear industry, I've listed them in this slide. So we have aqueous liquids, organic liquids, solids which are categorized as either compactable or non-compactable, and these arise in different processes and quantities and require a dedicated means of handling, processing and disposal. So nuclear waste pre-disposal. So the pre-disposal of waste covers a number of activities, so such as treatment, so means by decontamination, size reduction, cutting and compaction. Conditioning, which includes conversion of liquid waste or solid waste into a form suitable for packaging and disposal. Or immobilization, which is a means to convert liquid and solid waste into a passive form using things like cementation and vitrification processes. Storage is required in dedicated storage facilities suitable for the type of nuclear materials, and transportation as well. So either transporting waste across the nuclear site or for treatment and storage, or transportation of material off-site to other nuclear facilities. Decommissioning is also part of the pre-disposal management. So nuclear waste pre-treatment stages. So this is the initial step in nuclear waste management. It may cover a range of activities in the management of nuclear waste and require a period of storage before waste is suitable for disposal. So the considerations on selection of pre-treatment methods. So some consideration for selection of pre-treatments are due to the type of radioactive waste and also what radiological protection measures may be needed to be put in place to keep operators, the public and the environment safe. What waste minimisation activities are required, such as size reduction to remove what we call hotspots of activity for the segregation of remote handleable and contact handleable waste. There are also limitations on what pre-treatment technologies are available on each of the nuclear licence sites. And the economics, as I mentioned before, are based upon as low as reasonable practicable, LARP, on a risk-based approach. And there may also be requirements, further requirements for treatment, storage, transportation, and pending disposal. So nuclear waste treatment stages. So the basic objective for the treatment of radioactive waste is to minimise the volume, reduce the volume of nuclear waste, remove radionuclides from waste which may be harmful to the environment, or to change its physical or chemical composition by encapsulation of waste into a passive and form safe for interim storage and disposal. So here we have some examples as well in terms of mechanical treatment of waste. So compaction is using different types and designs of relatively simple compactors with a compressive force somewhere in the region of 10 to 50 tons to offer available varying volume reduction. So a drum is then compacted into a puck, and a number of pucks are then able to be put into another drum, and then grouted to immobilise this waste form to make it suitable for long-term storage pending disposal. So thermal treatment methods. So we're looking at incineration. Is normally achieves the highest volume reduction and converts the waste into a form which is suitable for subsequent immobilisation and disposal. And typically the volume reduction factors for incineration range from 50 to 100 times for solid radioactive waste, whereas if it's liquid waste, these are much higher, somewhere between 500 to 1,000. So other treatment methods as well may involve melting or chemical reaction, so and also biochemical and photooxidation decomposition. So two examples of conditioning are provided here. So either direct cementation, where a cement is added to a waste in a drum and a sacrificial paddle is used to mix the waste and the cement inside a steel drum, or a thermal treatment method, the vitrification process. So this one is a two-stage thermal treatment process where highly active liquor waste is converted to a powder form in a calciner and then mixed with molten glass to produce a vitrified waste, which is then poured into steel containers, which are then subsequently processed and stored pending disposal. So packaging of waste. So this is a fundamental process in the management of nuclear waste. Nuclear waste must conform with a packaging specification to be approved of for disposal. Low level and high level radioactive waste must be packaged in a form which is suitable for disposal. Typically, drums of encapsulated waste are put inside larger steel boxes, and then the boxes are then flood grouted. This makes the waste package suitable then for interim storage pending disposal. Transportation. So there are dedicated means for the transportation of radioactive material, which includes nuclear waste. Radioactive materials are transported in dedicated containers and flasks and on vehicles which have been designed or adapted to allow for the carriage of these containers and flasks. Radioactive material are permitted to be transported by land, sea and air. So in the UK, the direct rail services delivers rail transport of radioactive materials, which covers the length and breadth of Britain. The Pacific Nuclear Transport Limited as purpose-built ships, which allow for the transportation of radioactive material by sea. And just to say as well, the International Atomic Energy Authority has written the specific safety requirements for the regulation concerning the safe transportation of radioactive materials, and the definition and classification of packages for nuclear waste transportation are provided in these international regulations. And it's a legal requirement to use these safety standards, which have been adopted into UK law through UK legislation. So the different types of transport containers. So we have from low integrity, less hazard, through to high integrity, dealing with much more hazardous materials. So IP1 and IP2 containers carry large quantities of low specific activity objects. Type A designated to carry smallish quantities of the least hazardous materials. Type B being able to carry large quantities of the most hazardous materials. And Type C are the packages that we would call sort of superheroes of the packaging world. So these are designed to withstand falls or aircraft crashes. And then in terms of, so the Radioactive Waste Management Limited, which is now Nuclear Waste Services, has defined standard waste packages. So unshielded waste packages do not carry their own shielding. There are a number of waste packages which are unshielded, ranging from 500 litre stainless steel drums 3 meter cube boxes and drums, and also what we call the Miscellaneous Beta Gamma Waste Box, MBGWS, which is a variant from Sellafield to store miscellaneous beta gamma waste. ILW dose rates as well also require additional shielding, so which is carried in a transport container, and waste packages removed removed from the transport containers at the geological disposal facility, which allows them to be reused because they are significantly expensive. You can look at a transport container costing somewhere in the region of £1.5 million each. Some waste do not require additional shielding and can be transported in self-shielded intermediate level waste containers. So there's some further examples here of a shielded ILW waste containing transports as type IP2 transport packages. So these are shielded packages. Lower dose waste can carry their own shielding. So things like depleted natural low enriched uranium. There's many thousands of packages where there's no significant dose or criticality risk. Things like waste encapsulated into concrete directly into container. And there's a number of different types. So looking at sort of 4 meter box, which is a standard ISO, so International Standard Organization categorization of a container, 2 meter cube box, and 6 meter cubed boxes as well, which may be manufactured from concrete. So for all intermediate level waste, there's also some higher active waste as well that requires packaging. So these may be based on a welded copper cylinders, which aren't shown on this picture. So, and then we've got another RWM standard package here. This is called a robust shielded container. It's described as robust because the nuclear waste is inside the actual container is allowed to be packaged loose. All of the strength is provided by the container, and so it assumes no contribution from the actual waste form itself. So usually there's a balance between two, with both contributing to provide a protective effect. This robust shielded container is also called a ductile cast iron container, a DCIC, and mainly the shielding is controlled by weight, so low payloads, not especially efficient from a GDF point of view, and obviously cheaper stores require less shielding is required within these stores. And then the last one, so the Type C container. This is not a standard RWM package. It's just to illustrate that lots of different packaging types. This is the most robust type of container, and it's required to withstand a 90 millisecond impact. So this one is mounted on a rocket sled and then hard impacted at over 130 meters per second. So this is equivalent to a speed of about 290 miles per hour with no loss or dispersal of radioactive materials. So the concept of a Type C container is to enable airborne transportation of the most hazardous materials. And then storage and disposal. So the storage of nuclear waste involves mainly the radioactive waste, such as waste which is isolated, protected from the risk of discharge to the environment, and monitored as well to ensure that the packaging maintains its integrity. The storage may allow for radioactive decay of nuclear waste to reduce its radioactivity prior to disposal, or to allow for radioactive heat generated from irradiation to reduce over time. The cooling of radioactive waste is an important consideration, which may require active cooling, or storage facilities may be required to provide a means of passive cooling. So a nuclear waste disposal. So as we call a repository, So this is defined as an excavated underground facility that is designed, constructed and operated for the safe and secure permanent disposal of high-level waste. A geological repository uses an engineered barrier system and a portion of the site's natural geology, hydrology and geochemical systems to isolate the radioactivity of the waste. The disposal of effluent is permitted by approval of the authorisation for discharge to the environment, so both liquid and aerial effluent, by the Environment Agency in England and Wales and the Scottish Environment Protection Agency in Scotland, through the issue of an environmental permit in compliance with the environmental permitting regulations. So from a GDF, geological disposal facility, the nuclear waste may or may not be retrievable in the future. And the barriers that are used can either be natural or engineered, and a containment system can contain one or more of these barriers. So the disposal routes, so depending upon the radioactivity, different disposal facilities, each having varying degrees of expense and complexity, suited for the disposal of different nuclear waste materials. So spent fuel, plutonium and uranium are not currently categorised as waste, but may be classed as waste in the future. For the UK repository design, this has also included the requirements for disposal of spent used reactor fuel. So, mentioned before, a geological disposal facility. So for the UK government strategy for permitting one geological disposal facility for the UK, which excludes Scotland, which will be somewhere in the region of 1,000 metres below ground and cover 1 square kilometre on the surface. A GDF will be a significant piece of UK infrastructure, but the majority of the facility will be up to 1,000 metres underground. On the surface, a GDF will take up the area of about 1 square kilometre. The geological disposal is internationally recognised as a responsible for solution for disposal of nuclear waste for generations long into the future. There are 3 illustrative designs for a GDF based upon 3 geologies. So either hard rock, typically granite, evaporite, which is a salt, or a sedimentary, such as clay, host environment. The most challenging design for packages is that the hard rock design, so obviously requiring bigger caverns, bigger stacks, and bigger drops. The lines in the diagram represent the tunnels and shafts and vaults, and there are 3 distinct parts required for the GDF. So between shielded, unshielded and high heat generating wastes. This is in line with government policy for siting a GDF requires both a willing community and a suitable site to host it. So near surface disposal. So the NDA believes that there is a proportion of intermediate level waste that could be more appropriately managed in near surface disposal instead of GDF. This has been developed following recommendations by the Committee on Radioactive Waste Management, or CORUM. So what does near surface actually mean? Basically, this is an underground disposal which is less than 500 metres deep. So 2 main options are being considered. So at surface and tens of metres deep, so in the region of about 80 metres. Vaults, silos are all considered at sort of tens of metres deep. Only vaults at the surface, similar to design for low-level waste. Caverns seem to be unlikely, and vaults and silos are basically the same concept, just with more or less vertical depth. The depth of facility is considered based upon the decay time versus the erosion rate due to the risk of future glaciation. So this concept is favoured because it could save millions of pounds compared with deep geological disposal to build smaller and less costlier facilities, and to take some of the pressure off the GDF in terms of the availability of volume for it. The estimated cost of surface facilities with vaults somewhere in the region of £45 million. For deeper vaults, this could go up to somewhere in the region of £325 million for a facility. And then currently, these costs may be considered to be optimistic and are likely to rise in the future. So obviously, this would also take pressure off nuclear waste stored at nuclear licensed sites to allow for intermediate level waste to be removed from stores faster. This would then free up capacity for other intermediate level waste, which will be generated and possibly save the need to build more stores on existing nuclear sites. The near surface store will require a few decades of operational life and a management phase in the hundreds of years. There have been no proposed sites as yet, and there are also other concepts for near surface repositories, such as backfilling facilities with soil and concrete, as well as building cap structures over the top. But this would hinder the retrievability of the waste. So the low-level waste repository, we have a national low-level waste repository located south of Sellafield in Cumbria. This is a specially engineered facility with concrete-lined vaults for the disposal of low-level waste for near-surface disposal. Waste is flood grouted with cement inside steel containers. These steel containers are generally half-height isofreight containers, which contain low-level nuclear waste, and these are stacked until the repository can be covered with an engineered cap and closed to prevent rainwater entering and inadvertent intrusion. In the north of Scotland, the Dounreay site has its own low-level waste repository for waste from the site, and the nearby Ministry of Defence Vulcan Naval Reactor Testing Establishment. The current strategy is to divert as much nuclear waste away from the low-level waste repository, so to use as little of it as possible, favouring recycling and landfill. The low-level waste repository has a limited capacity for nuclear waste disposal, and it needs to be able to accept waste to support future decommissioning of the retired nuclear power stations and existing nuclear facilities across the UK. So some of the future challenges of nuclear waste: hazardous materials, so those containing contaminated lead or mercury will require some form of pretreatment before they can be recycled or disposed. Lead is present as a material to provide radiological shielding, generally in the form of bricks or sheets. Lead paint was also used as well until the 1970s in some nuclear facilities. There's also a significant quantity of radiologically contaminated asbestos materials, as asbestos was used extensively in construction materials to build nuclear facilities up until the late 1970s. So I'm going to talk a bit more about graphite in a further slide. The volume and quantity of intermediate level waste is very challenging, especially for the future plans to decommission all of the existing nuclear facilities in the UK, and also the capability to handle both remotely and contact handleable nuclear waste, and the capacity to store any of these waste produced throughout the decommissioning process. I've also included plutonium and uranium. So although not categorised nuclear waste, these are considered to be assets for future reuse to be able to make new nuclear fuel. So just a bit more on graphite. So the advanced gas cooled reactors. So this was a type of nuclear reactor designed and operated in the United Kingdom. These are a second generation of the British gas cooled reactors, using graphite as a neutron moderator and carbon dioxide as a coolant. These have been the backbone of the UK's nuclear power generation since the 1980s. The AGR was developed from the design of a Magnox reactor, which was the first generation reactor design. Since the irradiated graphite has resulted in the production of carbon-14 radionuclides, this means that it's a radioactive waste and may be considered to be unsuitable for disposal due to the presence of carbon-14, which is highly mobile and radioactive in nature. As a result of the nuclear legacy, there's a significant quantities of irradiated graphite, which now require a suitable disposal option. A number of high-level strategic options for the management of graphite have been laid out by the NDA in 2011, and the viability of these options were to either manage irradiated graphite as intermediate level waste and use the GDF for future disposal, or else to condition the graphite to allow disposal in either the low-level waste repository or to remove the bulk contaminants to all for some of the graphite to allow it to dispose as either exempt or free release for landfill, or to send the graphite to a separate disposal facility, including near-surface disposal.
Carl, we have just 2 minutes left.
You've got 2 minutes left, right? So I'll quickly run through then. Apologies. So the spent nuclear fuel. So the UK has not reprocessed all of the spent nuclear fuel it's generated. Since there's no longer a closed loop cycle to be able to reprocess the remaining spent nuclear fuel and the nuclear fuel that will be used in the future, a long-term solution for its safe disposal is required. And let me go on to the next one. And then last 2 slides. So plutonium, the inventory also includes some forms of plutonium, such as experimental MOX pellets and fuel assemblies from previous tests. This has been extracted plutonium by reprocessing at Magnox and Thorpe reprocessing plants. The plutonium stored in small cans due to the risk of criticality. It's not easy to combine uranium and plutonium into MOX fuel, and all of the stores of PU will now need reworking to produce reusable MOX fuel due to ingrowth of neutron poison radionuclides. So it could be used to produce mixed oxide fuel to be burned in nuclear reactors, or could be encapsulated into a waste for disposal for a future GDF. So we don't currently have the capability to treat this plutonium, so it would require significant investment, which is going to run into hundreds of millions and billions of pounds due to the need for security of special nuclear material and to comply with UK regulation. So uranium, which has been collected as waste material as well from tails of uranium mining and enrichment of nuclear fuel. So this is present as well in high enriched uranium from nuclear submarines, and is currently stored in 200-litre drums, and we have tens of thousands of tons of uranium held in storage in the UK, and no decision has been made by the UK government as to the future of this material. And I would just like to finish off by saying thank you for your attention, and I've put forward a few suggestions for future topics. So if people are interested, then let me know and we could maybe organise something else.
Thank you very much, Carl. It was amazingly interesting talk. I think everyone agrees with me. IOSH will be launching a survey in a minute, and could you please make your choice for the future suggestions and help us to choose which direction to take it from here. I'm afraid we don't have time for answering all of your questions. However, the recording and slides and Excel spreadsheet with Q&As will be available later on the IOSH web pages, and attendees will receive notification of it. Meanwhile, while people are answering survey, I think that we have time for one question. And Carl, the question that interested me too: if a low-level containment was bombed, what would be the implications? Asked by Jeff Smith.
So what if someone actually targeted
accidentally?
And accidentally, if it got exploded, or, you know,
yeah, if it's bombed, but we are in such a certain world situation, anything can happen. So what would be the implication if a bomb was aimed at the site of the low-level containment?
So you would get, obviously, you would get some contamination spread from the, from the explosion itself, but generally for low-level waste, it represents quite a low level of risk and harm to the public, and the dispersal of that material as well, the actual concentration would actually decrease. So it's probably not significant in terms of hazard. You'd be more worried if you're standing next to it when it exploded, to be honest.
Okay, so it will depend on the extent of the damage.
Yeah, absolutely,
okay.
yeah.
We do have a number of very interesting questions, so thank you very much for presenting. I will forward you the questions so you have an opportunity to address them, and people who ask the questions will be able to see the answers at a later date. Thank you very much, Carl. Thank you very much, IOSH members and our guests. And that's all for today. See you next time.